Hey everyone, and welcome to this explainer. Today, we are absolutely decoding the strict rules and the exact math behind series circuits. We're going to break down the logic and the calculations that make these single-path systems tick, and we'll be using this deck to guide our way. Let's jump right in. Here's a quick look at our agenda. We've got the language of circuits, rules of a series circuit, understanding Ohm's law, and then we're going to prove it all by solving the 110-volt and 220-volt problems. All right, starting things off with Section 1, the language of circuits. So before we can calculate anything, we need to know what we're looking at. An electric circuit is essentially a complete, uninterrupted path that allows electrons to travel. Think of it like a loop. It starts from a power source, like a battery, travels along a conductive wire, moves through a device, like a light bulb, and makes its way all the way back to the source. Without this complete, closed loop, those electrons literally have nowhere to go and absolutely nothing happens. Now, when we map this electricity out on paper, we use schematics. As you can see here, a resistor is drawn as a simple zigzag line, which perfectly represents the friction it provides. A conducting wire? That's just a straight horizontal line. Your power source, or battery, features distinct positive and negative marks. And a switch is drawn as a slanted line pointing upward, visually representing a break in the path that can be closed to let the current flow. Simple, right? Moving right along to Section 2, rules of a series circuit. The defining feature of a series circuit is that all the components are connected end to end. This creates one single, distinct path for the flow of electricity. The electrons traveling through this wire have absolutely no alternative routes. Zero. It is a strict one-way street, and they have to pass through every single component sequentially. And because of that single path, there are two golden rules you absolutely must remember. Look at side A. The current flowing through is exactly the same everywhere. If you measure the flow at the beginning, the middle, or the end, it is identical. But look at side B. The total voltage from the source is divided and shared among all the components. This is actually the exact opposite of a parallel circuit. In a parallel setup, the current branches out in splits, but the voltage stays constant across all those branches. In our series setup, though, think of current as the sheer volume of water flowing through a single pipe. It's totally consistent. But the voltage, the electrical pressure pushing it, gets chopped up and consumed by every single bulb on that path. Because there is only one path, finding the total resistance is remarkably straightforward. You just add up the resistance values of every single component along the wire. Total resistance equals R1 plus R2 plus R3 and so on. Every bulb you hook up simply adds more friction to that one uninterrupted route. Which brings us to Section 3, understanding Ohm's law. You can't talk electricity without Ohm's law. It dictates the relationship between the three main pillars. Current equals voltage divided by resistance. Basically, current is directly proportional to voltage. So if you use a bigger battery with more voltage, your current goes up. But it's inversely proportional to resistance, meaning if the resistance goes up, like by adding more bulbs to our single path, your total current naturally drops. Let's see this in action. Section 4, solving the 110-volt problem. Picture this setup. You've got 4 completely identical light bulbs. Each one has a built-in resistance of 140 ohms. They're wired together in a strict series path, and they are being powered by a 110-volt source. Our goal is to figure out exactly how the electricity behaves across this entire system. To do that, we're going to follow these 3 exact steps. Step 1, find the total resistance of the whole path. Step 2, find the total current flowing through the circuit using Ohm's law. And step 3, calculate the individual voltage that each specific bulb receives. Step 1 is a total breeze. By simply adding the resistance of our 4 140 ohm bulbs together, so 140 plus 140 plus 140 plus 140, we get a total circuit resistance of 560 ohms. Moving on to step 2, let's apply Ohm's law. We take our total voltage from the source, the 110 volts, and we divide it by the total resistance we just calculated, which is 560 ohms. This gives us a total electrical current of 0.196 amps flowing straight from the battery. And remember our golden rule of series circuits? Current is the same everywhere. Walang nakakalamang, as the phrase goes, no one has an advantage. Because it's a single path, the very first bulb in the line gets the exact same 0.196 amp flow as the very last bulb. They are all completely equal. Now for step 3, finding the shared voltage. By rearranging Ohm's law just a bit, we multiply the 0.196 amp current by the 140 ohm resistance of a single individual bulb. This shows us that each bulb receives exactly 27.44 volts.
And here is the truly beautiful part. If you add 27.44 together 4 times for all 4 bulbs, it perfectly adds back up to roughly 110 volts total. The math literally proves the theory.
Let's turn things up a notch. Section 5, solving the 220-volt problem.
This time, we're dealing with 8 bulbs in total along a single wire. Now, unlike a parallel circuit where the load would be branching out, these are all stuck on one continuous path. 4 of these bulbs have 80 ohms of resistance, and the other 4 have 100 ohms of resistance. All 8 are sharing a much larger 220-volt source. Just like before, step 1, we sum up all the resistance. We add the 4 80-ohm bulbs, which totals 320 ohms, to the 4 100-ohm bulbs, which gives us 400 ohms. Adding those two groups together gives us a grand total circuit resistance of 720 ohms. For step 2, we divide our 220-volt source by that 720 ohms of total resistance. That gives us a universal current of exactly 0.306 amps. And despite the bulbs having different resistances, that 0.306 amp flow is exactly the same everywhere on the wire.
But step 3 is where this gets truly fascinating. When we multiply that universal 0.306 amp current by the individual resistances, we uncover a core truth about how voltage is shared. On side A, the 80-ohm bulbs receive 24.48 volts each. But look at side B. The 100-ohm bulbs actually receive 30.6 volts each. In a series circuit, components with higher resistance actually claim a larger share of the total voltage. They literally take more of the electrical pressure. All right, so with all that math out of the way, I've got a practical question for you. Imagine you have this 8-bulb setup running right in front of you. What happens to the brightness of the remaining bulbs if you bypass and completely remove one bulb from this series circuit's voltage sharing equation? The remaining bulbs actually get visibly brighter. Since they suddenly have fewer components to share that total source voltage with, each remaining bulb gets a larger individual slice of the 220-volt pie. But this also reveals a huge, fatal flaw. If one bulb physically breaks, the single path is severed and the whole thing goes completely dark. And this, right here, is exactly why our houses are wired using parallel circuits. In a parallel setup, the electricity branches out. If you remove a bulb, the other branches just keep working. And because voltage is constant across parallel branches, the brightness of your other light stays exactly the same. It's a real game changer. So next time you flip a switch and only one light comes on, be thankful for parallel branching. Thanks so much for learning with us today.